build a strong and supportive community of students passionate about competitive programming and problem solving. It's great to see all of you here with us again, whether you've been with us since the first awareness session or are joining today for the first time. You're now a part of a growing community. You're now a part of CodeX. I am Yashoda De Silva, your moderator for today's session, representing the CodeX Sri Lanka team. I'm excited to guide you through another valuable session in your journey towards becoming a better coder. Now, before we dive in, let's quickly revisit what we did last week. Last week, we held a technical hands-on session led by Mr. Apiram Rajamohan. It was held on the 12th of July with over 70 undergraduates from universities across Sri Lanka. The session provided practical insights into two pointers, arrays, and prefix sums, laying a strong foundation for competitive programming techniques. The attendees received valuable tips on how to get started with problem solving, equipping them with strategies to tackle coding challenges effectively. It was an interactive and engaging session encouraging active participation and peer learning throughout. And before we begin today's session, a quick reminder to everyone. As you all know, certificates of participation will be awarded at the end of the CodeX session series based on attendance and engagement. To support this, please make sure your Zoom name matches the name you used during registration. This helps us track participation accurately. I repeat, please make sure your Zoom name matches the name you used during registration. This will help us in tracking your participation accurately. Thank you for your cooperation. Now on to today's topic. Tonight's session will cover sorting algorithms and binary search, techniques that appear frequently in contests and interviews. Mastering these will give you a major edge in solving problems efficiently. It is with great excitement that we welcome a truly inspiring individual to kick off our third CodeX session, Mr. Lakshith Nishshanke. Mr. Nishshanke is a software engineer at Zaya, a competitive programmer ranked second in Sri Lanka at IEEEXtreme 18.0, and also an experienced participant in global coding competitions. He is also a passionate mentor and a competitive programming educator, committed to empowering the next generation of problem solvers. With his remarkable achievements and deep experience in the field, we're truly privileged to have him share his insights and wisdom with us today. Please join me in warmly welcoming Mr. Lakshith Nishshanke to CodeX Sri Lanka. We are truly honored to have you with us, and we are looking forward to an engaging and educational session. Over to you.
Hi, can you guys hear me?
Yes, Mr. Lakshith, you're audible and we can hear you and see you as well. Good luck with the session.
Nice. Thank you. Nice. Give me a minute. Okay. I think you can see my screen too now. Can you?
Yes, the screen is visible.
Yeah, nice. Hi, so hello everyone. So Today we are going to talk about like searching algorithms and sorting techniques related to competitive programming. So yeah, uh, this is not like a really long lesson, so let's get started. Yeah, so about me, I'm Lakshith, and I've been doing competitive programming for like more than 5 years now. Mm, and yeah, that's it, I guess. So yeah, like the last session, I did the plan here is like going through high level stuff. You all can investigate further. And I won't be like this won't be like a lecture because I don't think that really works. Mm, yeah, okay, so let's get started. So okay, sorting. Uh yeah, sorting is like I think everyone knows what sorting means. Sorting is like basically you are given a set of elements, a list of elements, and then you have to order them by some kind of a metric. So that's what sorting is. And with respect to like computer programming, sorting is like a fundamental step of problem solving. Like most of the like problem solving techniques, you'll have to like sort the numbers first. Uh, yeah, like sorting is like extremely common. Like almost all the problems you'll have to like do some kind of sorting. Yeah. Yeah, so that basically means creating an order of items. So for an example, in the image, we have like BDAC. If we sort them, it's going to be like ABCD. Yeah, it's a pretty simple thing, right? Uh, yeah, please ignore the title. I, I was changing my last presentation slides and maybe I forgot to change the title. Oh, no, it's a correct title. So my bad. Sorry. So when you're done with sorting, when you're done with sorting a list of elements, they have to be like a monotonic order. So, for an example, if we sorted an element in ascending list of elements in ascending order, uh, like the every number must be like greater than or equal to the number before, right? And another thing is like these are like kind of formal definitions. You don't really have to pay attention. Uh, when you're done with sorting a list of elements, that list must be a permutation of the original. So permutation means like the original elements, all the original elements must exist after sorting. Only the order can be changed. So yeah, these stuff are for like concrete definitions, but like, sorting is still a simple thing. Yeah. So when talking about like sorting numbers, we have to focus about a couple of things. One thing is time complexity. That's probably the main thing. And then we have space complexity. And there's this thing called online versus offline. And there's also this thing called stability. Mm, yeah. Let me talk about like sorting algorithms a little bit more first. So like I said, I don't really have to explain sorting much more. I guess it's a simple thing, right? And since it's common, uh, it's like a very popular problem to solve. And for that, there are like lots of ways to go about that. So we have like so many sorting algorithms, and all of them have different properties, like slightly different stuff in each algorithm. And you don't really have to know about like all the sorting algorithms if you are like doing computer science or maybe in software engineering. In your modules, maybe you will learn some sorting algorithms. Like first you will learn like bubble sort, yeah, and then merge sort, insert. So there is a couple of sort like popular sorting algorithms. You will learn about them. And uh, like in this session at this point, what you have to know is sorting is like a clear thing, right? And there are like multiple ways to solve it. And for those algorithms, there are different time complexity and space complexity properties. And since this is like the third session, I think you have like a rough idea about what time complexity is. Yeah, I also taught that in the first lesson, I think, a little bit. So yeah. So here I'm showing like a couple of sorting algorithms. You don't really have to know at this point how these work. And then also about the time complexity. This is the photo I found from Google. You can ignore the best case and average case. So like I said in the first session, we are only concerned about the worst case time complexity. So you can see that this bubble sort has n squared, selection sort has n squared, insertion those has n squared, and the merge and heap sort has n log n time complexity. And then they also have like this space complexities, like bubble and selection sort has like linear space complexity, not linear, constant space complexity, and quick sort and merge sort has linear complexity. So what I'm trying to say here is there are like different algorithms with like different properties, time complexity and space complexity. You might not know what time and space complexities mean. If so, you don't really have to focus on this. Let me let me explain it real quick. So, by time and space complexity, what we mean is like, so with time complexity, what I mean is how long it takes to run the algorithm with respect to the input size. So imagine we are saying seconds. So if the input size is 10, this will take 100 seconds. If the input size is 10, this will take like log base to 10 is 3, like 30 seconds. So the n log n is like this merge sort and heap sort is faster than the other bubble sort, selection sort, insertion sort, like those. So that's basically what time complexity means. Space complexity logic is also similar. Uh, you don't really have to know everything. If you know, that's good. If you don't, that's okay. What I'm trying to say here is some algorithms are better than some other algorithms. And also there are some trade-offs there. So for an example, the bubble sort is slower by the time, but the space required for the bubble sort is like really low. So this merge sort is like faster than bubble sort, but it will need more storage. Yeah, so there are different algorithms with like different properties and different advantages and disadvantages. Okay. Mm, and next I thought about like uh, first going through like a sorting algorithm, a simple one just to explain how it works. I think if an university, the first sorting algorithm they teach is bubble sort. Uh, I'm gonna like quickly go through it. There are like so many resources online, so I don't think like we, we shouldn't be like spending that much time on this session. Uh, so yeah, so bubble sort is basically you are going through the array, go. You have a list of numbers. You want to sort it. So this is one way of sorting that. It's called bubble sort, and the way you do it is you are gonna iterate through the array, and then whenever you find some like mismatching elements. So for an example, if you're sorting this in ascending order, uh, in the initial step you can find 5 and 3, but it shouldn't be like that, right? Because if it's in the ascending order, 3 should be before 5. So what you do is whenever you find something like that, you swap them. So we see that 5 and 3, we see that, and in the next step we switch that into 3 and 5. Then we see 5 and 8, we again switch that. Oh no, we don't switch that because 5 and 8 it's okay. And in the next step we see 8 and 4. That shouldn't work because 4 should be before the 8, so we switch that. And then we see 8 and 6. Uh, we switch that. So we get 6 and 8. So I think this step is clear. What we're doing is we have a list of numbers, we are going through it. Whenever we find like a mismatching pair, we swap it, sub that. So I hope it's that step is clear. Uh, does anyone have any questions? Like, are there any unclear stuff? Well, we're gonna find the chat. Okay, I have the chat open. So if you have any questions, you can ask. Okay, I guess it's clear. Uh, if anyone have any questions, just ask. So we keep doing that, and you can see at the end we have 8 here. And if we go through the array doing this operation, at the end we have like we can guarantee that one element will be in its correct place, because the maximum element will be like moving forward, like going to the last place. So when we do this once, we can guarantee that one element going to be in its correct place. So what we do is we do the same operation, the one I described, n times. So if we keep doing that, we are going to end up with a sorted array. I'm just quickly going through the sorting algorithm. Is that clear? One the reason why I'm like quickly going through sorting algorithms, like even though the station's name is like sorting and stuff, so I have to go through sorting algorithms, you might think, but the thing is, like, for competitive programming, you don't really know how to write an algorithm yourself, like a sorting algorithm by yourself. So it's not like super important, but you should know like a basic idea on how this works. So that's why I'm quickly going through it. Uh, if it's like super clear, it's okay. So does anyone have any questions? You'll think of questions and I'll turn on the fan. It's too hot here. Yeah. Between on the fan, so if you all can hear noise and it's too distracting, let me know. So I guess this is clear. Well, if someone has any questions, just drop a text in the chat. Okay, then we have merge sort. I'm also going to like, oh, maybe I'll go to message. Okay, clear, nice. So we also have merge sort. So merge sort is like a sort of a complicated algorithm. Uh, the technique here, the technique used is called divide and conquer. Uh, the way we are doing this is at each step, we are going to divide the array into two parts and keep on dividing that until we get one element, and then we keep merging them. The logic behind here is the merging part. If we have two sorted arrays, we can merge them together in linear time. So that's the logic here. And since we are like at each step, we are dividing the array into two parts, we are going to reach from here in log base to n. Like if the array size is n, we can reach here in log base to n levels. So again, here log base to n levels. And for each step, we are going to do a merging. There will be n elements. So at each step, we are going to do a merging of like n operations. And we have log n height, log n into n log n. So the time complexity here is log n. This is like an extremely high level walkthrough. Uh, my plan isn't here to like exactly teach you how merge sort works, but if someone's curious, like I can go into more details. Does anyone want to know more details? Okay, can you go a bit deeper? That's okay. Right. Okay. Yeah. So I'm asked to like explain a bit more on this. So yeah, do I have other slides on this? No, right? This is just one. Okay, so uh wait. Guys, give me a minute. I'm thinking of the clearest way to explain. Okay, so in the bubble sort we had yeah, in the bubble sort what we did was like we are doing some operations on the array once and then repeating that n times to make sure the entire array is sorted. So that in that sorting algorithm we have n squared steps. The goal here in the goal is merge sort to like reduce that. And the technique we are using here is called divide and conquer. I said all that. So basically, divide and conquer is like whole other topic. So basically, what that means is we are dividing the problem into smaller components and then solving them and merging them together, hoping it lead to a better time complexity. Like we should be able to sort the array in like low number of operations. Okay, so and another thing is like like background information for that. Imagine if you have two sorted arrays. If you have two sorted arrays, you can merge them together to create another sorted array in operations. In as in like if one array has n elements, if other array has m elements, you can create a sorted array combining both of them in n plus m operations, like linear time complexity. The way you do this is uh, you are going to keep a pointer, you're going to keep two pointers in each of the arrays, and then you're going to keep compare the pointers and see which array has the smallest element, and then add the smallest element to a new array. And then better if I can draw it. Can I draw on Canva? Oh, I can. No, I don't think. How did I can? But am I sharing my memes? Did something happen? Wait, you guys can still see the screen, right? Okay, I can. How do I erase? Okay, so imagine we have this array. We have this array of 3 elements, and then this array of 3 elements. It is guaranteed that both of these arrays are sorted. And then we want to create a third array that is also sorted, combining both of these arrays. So that's the goal here. That's what we want to do. The way we do this is we are first going to like keep an array with like 6 slots, and then we are going to keep a pointer here, and we are going to keep a pointer here. And then we compare these values and figure out what's the smallest one and add that to here. Imagine this is the smallest one. We are gonna add that to here. And then we are going to move that pointer here. So we are comparing this and this. And then from those we are gonna put the smallest one. Imagine this is the smallest one. We are gonna put that here. And then we are gonna move this pointer here. And then again compare this like that. We are going to keep 2 pointers and we are going to compare it in both arrays and then figure out what's the smallest one there and put it to the resulting array. The logic behind this, since this array is sorted, like if we are focused on this element, it is guaranteed that all the elements to the right are greater than that. And same in the above array. And since therefore the only comparison we have to do is like the between the elements in both of the arrays, like to figure out the smallest element in across all 2 arrays. So that way, this pointer will move here. Like if this array is like the length is n, is going to move n times. If this array's length is m times, length is m, this point is going to move m times. So the total time complexity will be n plus m. If you know about time complexity, that means we can merge 2 sorted arrays to create the resulting another sorted array in linear time, n operations. So that's like background information. So we can merge 2 sorted arrays in linear time. So in merge sort, what we are going to do is we are going to keep dividing the array into 2 parts. Like here we have this array. We are going to divide this array into 2 parts, and again divide into 2 parts. Keep on dividing until we get a set of like unit elements, and then like by definition element a list of length 1 is sorted, right? Because it's just that element. So by definition, all of these elements are like considered as lists. They are sorted. So what we are going to do is merge those. We can merge them in linear time. Basically, we just have to compare these 2 numbers, right? We can merge it into like 27 and 38. For the 43 and 3 part, we can merge it to 3 and 43. Like that, we are going to merge everything. And then we are going to merge those again. Like we have 27, 38 and 343. We are going to merge that into like 3, 27, 38, 43, like that. Wait, if I explain the merging algorithm here, so what we are going to do is we are going to first keep a pointer here and then here for the both arrays, and then we compare those. 3 is the smallest, so we move the 3 here, and then we move this pointer to 43, and then we compare 43 and 27. The 27 is the smallest, right? We move 27 to here. And then since we picked this element, we are going to move the pointer to the right. And then we compare 43 and 38. We are going to move 38 here. And then there are no more elements. So we are going to move the 43 here. So that's the linear merging thing I explained. So like that, we are going to keep merging. So we are going to keep breaking, and then we are going to keep merging since these are sorted and we are merging into sorted arrays. when we are done with the merging and when we are getting a full list of elements, that list is sorted. So that is the merge sort algorithm. Is it clear? Were there any like confusing parts? Okay, nice. Okay. Okay, so now I'm going to talk about like this concept in sorting algorithms. It's called stability. Stability is sometimes when you are sorting list of elements, the value we are sorting might be the same, but those elements might be different. So imagine in a card deck, uh, there can be same numbers, but here you can see there's a 5 of hearts and there's a 5 of scores. So this is 5. So if we were to sort, those two will have like the same priority, but they're like different elements. So in those cases, some sorting algorithms could like jumble the order, like as long as the sorting algorithm is concerned, they're concerned about the number, right? Like imagine we are sorting this deck of cards by their number. So technically, if we were to sort 7, 5, 2, 5, and 2 to this, it's like technically correct, right? Because it's 2, 5, 5, 7. The order is correct. But there was like a previous order that the part was like before this, but in the sorted deck, it's swapped. So being stable means uh, even though they have the same priority as far as the sorting algorithm is concerned, if there was like a initial ordering of those elements, that ordering should be preserved. That's called being stable in the context of sorting algorithms. So basically, sort equal elements. So as far as the algorithm is concerned, these two cards are equal, right? Both are 5. Sort equal elements in the same order that they appear in the input. That's called being stable. So the practical use is that this might be important to like preserve the order of like the multiple sorts on the same data set. So like if you're sorting like a set of integers, there's only like one metric, right? We only have to sort by the value of the integers. So we are sorting like some complicated elements. They might have different properties, and we might have to sort them under like different conditions. In those, we might need to like preserve the order. Like even though the values are equal, we might want to preserve the order because elements are different. So in those, we'll have to use like a stable sorting. So when you're solving problems, some problems require this, and you just have to know that merge and bubble sort are stable algorithms, and there's also this sorting algorithm called quick sort. It's not a stable algorithm. So if you're ever deciding what to use, and this you have to pay attention to this. Like yeah, remember that merge and bubble are stable, like quick sort is not. And okay, another thing. So we went through some sorting algorithms and some logics, and yeah, we learned a little bit about bubble sort and merge sort. And so what algorithm should you use? Well, let me check. Okay. So the thing is, there are like lots of algorithms to sort numbers, sort elements, but there are only like a couple of standards. And most of the times you won't even have to implement them, because like almost all programming languages in the standard library of all programming languages, there is a sorting function. So you just have to call like sort, like just a function. Yeah, so you don't really have to remember those functions. Yeah, and there are also some weird algorithms, like weird sorting algorithms. You might have to remember those because there are problems you can use with those weird algorithms. So basically you only have to pay attention on the couple of standard stuff and the weird stuff. The couple of standards you won't really have to implement because all programming languages like provide implementations for them. So you don't have to write manually. And yeah, so remember that in the time complexity I mentioned, uh, some algorithms had like same time complexity, but even though like this is kind of a theory part. Basically, time complexity means the way the time consumed grows with respect to the input size. So even though two algorithms have the same time complexity, there are other constant factors that affect like the actual time spent to run the code, and that might be like slightly different. Uh, if you know about time complexity, when we are calculating time complexity, we are doing only an estimation, and if there are like constants, we are ignoring that because we are only concerned about the growth. So average case of insertion sort and merge sort both are logged in. But as you can see in this graph, for lower input sizes, insertion sort is faster, and then for like larger input sizes, merge sort is faster. No, I think insertion sort is actually n squared, right? Yeah, insertion sort is actually n squared. So n squared algorithm is supposed to be like much slower than the n log n algorithm, right? But even if the time complexity states that when the input sizes are small, that every algorithm has like constant factors about the time complexity. So for small input sizes, insertion sort might be faster because of all the constant factors. Um, kind of a theory part. Won't really matter. I'm not sure if you'll have to deal with this in a competitive programming problem. But what I'm trying to say is, yeah, like even though they're like there are more to it than the time complexity when you're deciding even about the time. So yeah. Okay. We have another sorting algorithm. This is a weird sorting algorithm. So it's called count sort. Uh, so this count sort thing was not even in that table. Yeah, there's no count sort here. These are like the most popular sorting algorithms. This bubble sort one nobody uses, selection sort nobody uses, insertion sort like for small input sizes you can use. This quick sort, merge sort, and heap sort, they are implemented in like standard libraries. Yeah, I don't know which languages sort functions uses which algorithms. I'm not sure. You might have to Google, but these are like the most popular one. And then this count sort algorithm is what I call a weird sorting algorithm. Wait, what happened? Oh, I think my browser crashed. Can you just give me a minute?
Mr. Lakshit, you're audible and your presentation is not visible, but your video is visible.
Ah, yeah, my browser crashed. We have a lot to cover. Okay, we have a lot to cover actually, and there's not that much time left, so I'm gonna go fast. So basically, okay, so we have this sorting algorithm called count sort. It's not popular because it's actually very slow, but for some test cases, it might be like really fast. The time complexity of count sort is like order of n plus k, where k is the number of distinct elements found in the array. So for an example, if you have this array, uh, this only have like 1, 2, 3, 4, 5. So this only like 5 distinct elements. So the idea behind count sort is, since there are only five types of element, we are gonna count like how many number of elements are in like each type. So then we are just gonna like duplicate that number like the counted times. So we are gonna count how many zeros are there. There are 1, 2, 3. There are 5 zeros and there are 3 ones. There are 4 twos like that. So what we are gonna do is here we create a sorted data array. That means we are creating like 5 zeros, 3 ones, 4 twos, no threes, and 2 fours, like that. Yeah, so when the number of distinct elements are low in the array, we can use this. In that case, it's going to be like really fast. But like in the general case, this is going to be like really slow, because imagine if you are sorting a list of integers. Integers can have like 4 into 10 to the power 9 distinct elements, I think. If so, 10 to the power 9 time complexity is like really slow. So you can't really use the count sort in the general case, but in some problems you can use this, like if the number of distinct elements are low. So this is kind of an interesting thing. So if you have any questions, I'm not gonna wait because we don't have that much time. If you have something asked, I'll come back. Okay, so by the way, if you know about time complexity, or n plus k actually looks like a linear complexity, but it's actually exponential. Uh, if I quickly say about that, it's because the time complexity is supposed to be like a function of the input size as in like the bit size. So if we consider the bits, then the number of distinct elements changes, the time complexity becomes exponential. This is also a theory part. You don't have to focus on that. Uh, if anybody want to know the math, just ask me. Apart from that, what you have to know is like that this, in the special case of like having a low number of distinct elements, this sorting algorithm is really fast. In the general case, this algorithm is like extremely slow. You should use this. Okay, so the bucket sort is an extension of the count sort algorithm. What we are doing here is we are going to keep like make buckets of like ranges, and then fill those buckets with the numbers, and then do a normal sorting algorithm and sort the buckets. And then since these buckets are in order, we can just like merge those. It's also pretty self-explanatory, I think. If anybody have any questions, ask. Okay, another theoretical point. We saw that for some sorting algorithms, the worst case time complexity was order of n log n. And actually, that is the theoretical lower bound of a generalized sorting algorithms. We can't go lower than that. Like that's the best we can find. Okay, so about when we are using sorting algorithms, most of the time you won't really have to implement them unless it's like a special problem and you will have to implement a count sort or a bucket sort, or there's other things, other like sorting algorithms like that are called like there's a radix sort. Yeah, there are some stuff like that. unless you're doing something specific like that, you don't really have to sort, like you don't really have to like implement sorting algorithm by yourself. And like if you want to change the behavior of a sorting algorithm, like you can use ascending, descending, or do a weird thing inside the when comparing two numbers. You can actually override the comparator. Like in the sorting algorithms, you can, like when you're using a sorting algorithms from a standard library in all languages, you can just specify if we were to do something weird with when comparing two numbers. So you can do that. I'm not going to like go deep about this. Whatever programming language you're using, just search how to override the comparator. You'll find some resources. And there's this website called sortingalgorithms.com. You can go there and visualize sorting algorithms. To like you can visualize how the sorting works and you can learn. Yeah, those are the tips about sorting. Okay, we are done with sorting and now we are at searching. Okay, so searching. So searching is also like something everybody does. So basically what we're doing is we're searching for something in a list, searching for any element in a list. So there are two methods to do that. Not two, there are multiple ways, like the most popular one, linear and binary search. Okay, so linear search is basically the most naive thing you could do. Like you're given a list of numbers and you're asked to find if there's an element in it. So what we are gonna do, you're gonna traverse the array and find out if it's in it. So that's a naive thing you could do, right? So that's called the linear search. And in the worst case means like the element you are finding is like, yeah, at the end of the array, or maybe it doesn't exist. If so, you'll have to go through the entire array. So in the worst case, the time complexity is n. The best case is when you try to find an element, you find that element in like the first place. So it's going to be like a constant time operation. So best case is like order of one. The worst case is like order of n. So that's the linear search. I think it's the most simple thing you would ask for. Okay, binary search. Binary search is like actually much faster than linear search. But the thing is, you can only do it in sorted arrays. So it doesn't really make sense. Like if you get an arbitrary array, you can't do binary, like sort it and do binary search, because sorting takes n log n times, and doing binary search on that takes log n times. So you can just do a linear search and find the element in linear time. So if you get a already sorted array and you have to do a search on it, you can do a binary search. Binary search is also like a super common problem type. So it's like a really important to know this. So in the worst case of the binary search, it's going to be like log n, not n. So log n is like log base 2n. So it's like really faster than the linear search. The way this is implemented is, I think I have to, okay. Yeah. The way this is implemented is, okay. You have a sorted array. You are searching for a number. What you're going to do is you're going to keep 3 pointers, like the left bound of what you're going to pick a range. You're going to set a left and right for that. And then you're searching in that range. So at first you're searching the entire array. So the L will be the first element, R will be the last element. Then what you're going to do is you're going to pick the middle element and then see if the middle element is equal to the element you are looking for. If it's equal, yeah, you find it, search completed. If it's larger than, like imagine if you're looking for 22. So you have L here, R here. You are going to look at this 36 and 22 is lower than 36. And since this array is sorted, that element should, if it exists left the middle element. So you can like by a single comparison, you can like get rid of half the array. So when you check 36 and 22 is less than 36, 22 cannot be in the right to the middle element. So you can like ignore all that half. So like that, by each iteration, we can reduce the size of the array by half. Like if in every step we half the size of the array. So like in the merge sort, when we go like dividing the array size by 2, at the end we are gonna reach a size of 1. The steps we need to do this is log base 2n, because we are dividing by 2. The math part, if you don't really understand, it's okay. So yeah, that's the binary search algorithm. Let me explain a bit more. So imagine you're looking for 7, and this is the sorted array. So at the at first, this is the left element, this is the right element, this is the middle element. We are going to check the middle element. So we are looking for 7 and we are looking at 14. Since 7 is less than 14, we know it's in this side. We can ignore all this side. And then in this side, we are going to take the 8 as the middle element. Why are we taking 8? 1, 2, 3, 4. Yeah, because 1, 2, 3, 4, 5, 1, 2, 3, 4. Yeah. Okay, let's say we took 8 as the middle element. So we check 8 and we know 7 is still less than 8. So we can ignore that part of the array. And then we are left with this part of the array. And then wait. I'm confused. 6 is the middle element. Wait. Okay, so I got confused and I probably made all of you confused too. So let's do this again. Yeah, your raised hands, I can see. I can't see any text. Can you talk or something? Or drop a text? Okay, I'm going to keep going. If you have anything to ask, drop a text. So I'm sorry, like ignore everything I said about this example. So yeah, we are looking for 7. This is the middle element we are looking at. So 7 is less than 14. So we are going to ignore this part. And then we are left with these elements. So we have 1, 2, 3, 4, 5, 6, 7, 8. And the middle element here is can be 6. Okay. Now we are looking at 6. We know that 7 is greater than 6. So it should be here. So we can ignore these. And then from these 4 elements, we are going to get the yeah. We are going to get 8. We know that the 7 is less than 8, so we can ignore this part and we are left with this single element. We are going to compare that and that's 7. So we found out that the array has 7. So in the linear search, we'll have to like go through all these elements and check what's there. But in this, we only did like 1, 2, 3, and 4 comparisons. So this was like much faster than the linear algorithm. So yeah, I didn't mess anything up this time. I think was it clear? Do you all have any questions? Yeah, this is still. Yeah, I'm gonna go forward. Okay, so there are a couple of terms that I wanted to talk about related to binary search. It's called lower bound, upper bound. So if you're using C++, there are two functions called lower bound and upper bound. They implement the binary search algorithm. So lower bound basically means position of the first element that is greater than or equal to k, like a given k. Upper bound is position of the first elements that is greater than k. So I might have a photo for that. Okay, yeah. It's going to be confusing though right now. So yeah, so in an array, lower bound k means position of the first elements that is greater or equal than k. Okay, we have an array here. Okay, imagine this part has k elements, like all these elements here are k. If so, lower bound is position of the first element that is greater than or equal to k. So here's the lower bound. So I don't know how to undo. Okay. Yeah, I don't know. So and lower bound and upper bound, like you can combine those and get a half interval of the array of elements that are equal to k. Yeah, don't focus much on that. There are two functions called lower bound and upper bound in C++, so you can use them directly to implement the binary search. So that's why I want to mention that here. Like you don't even have to like implement that algorithm by yourself if you're solving a computer programming problem. Yeah, let's skip this. Okay. Last, I want to talk about the binary search implementation because the logic behind binary search is like simple, right? You have a sorted array. You are gonna divide that array like half it in every step and figure out the element. But the thing is, when you're implementing this, there can be like edge cases. Sometimes like you might be writing a loop and it never ends. Sometimes it ends at the wrong position. Like there are like very minor details that affect this, making this like a really pain to implement. So there's a site called CP algorithms. I added a link there, so you can just search CP algorithms by research or something. So you'll get there, and they explain the implementation pretty clearly. So yeah, basically what they're going to do is they are going to maintain a like the left right. They said they are going to maintain a pair such that the element k will be in the range L and R, but it like this is called open range, right? I think so. The element could be in L, the element cannot be in R. Yeah, like this. The AL greater than less than I don't even know how to say that. So basically what I'm trying to say is when we're keeping the L and R, the element we are searching for is in the range between L and R minus 1. The R is like out of range. That's how we maintain the pair. The reason we are doing that is when we're actually implementing, that implementation requires like less corner work. So we can write a really small algorithm. So this is all the code that's required to implement the binary search. This is in C++, but it's only like if statements and like variable assignment. So it will work on like it's pretty simple. You can convert into any language. Yeah, and okay, so yeah, at the start you will have to like set the L to -1 and R to N. This is a zero indexed array, and then you are gonna like write a loop until the R minus L greater than or equal to 1. That means like if they're in the range you are checking, there has to be more than one element to check. If so, like we discussed, we are gonna find the middle point. You can find the middle point between two indices by like adding them and dividing them, and we are gonna compare it. We are gonna compare it and uh, move the range to like the left and right. Was that clear? Can someone ask if it's not clear? You don't really have to implement it the same way, but the thing is you'll have to like look for edge cases and corner cases when implementing. And if you're using C++, you don't really have to implement this. You can use the lower bound and upper bound. I personally don't use those functions because I always forget what's the lower bound, what's the upper bound. It is, I don't know, it's messy. So I end up implementing the binary search algorithm all the time because it's like slow. Not slow, it's like, sorry, small. Doesn't take that much time. Is it clear? If it's clear, I think this is the last slide. Yeah, thank you. Do you guys have any questions about anything I said? Okay, then it's all good, I guess. You can, I'm going to stop the screen sharing then.
Thank you, Mr. Lakshith, for that structured and informative session. You've helped break down complex concepts into digestible strategies that we can start applying right away. We have the floor now open for a brief Q&A session. And for the participants, if you have any questions about the concepts discussed or competitive programming in general, feel free to drop them in the chat. I believe there aren't any more questions. So thank you once again, Mr. Lakshith. Your explanations were not only clear, but practical and relevant to our audience. And your passion for teaching was truly evident throughout the session. I think we're facing some technical difficulty, but on behalf of the IEEE CodeX Sri Lanka team, we'd like to present you a token of appreciation. Unfortunately, we are not in a situation to display the token of appreciation through our presentation. But thank you so much for being a valuable part of our journey, Mr. Lakshit, and for investing your time and expertise into developing the next generation of programmers. And looking ahead, we've got another technical hands-on session coming up on the 19th of July. So stay tuned, and we'll be updating you through our social media channel and, of course, our website. If you haven't registered yet for the IEEE CodeX Sri Lanka session series, head over to our official website where you can learn more about the competition, track your progress, and get to know about session updates. So the links will be shared through the chat, and I hope you can access them there. And with that, we will conclude today's session. Thank you for joining us and actively being a part of this. Each session takes you one step closer to becoming the confident problem solver you want to be. We hope you found today's discussion both practical and inspiring, and we'll see you again very soon in another upcoming session as we continue to unlock new techniques together. Until then, stay curious, stay consistent, and keep challenging yourself. Good night, everyone, and thank you once again.